In this lesson, we are going to develop the concept of the natural base to use with our discussion of logarithms. So first, let's consider the expression 1 plus 1 over n to the power of n. And we're going to complete the table for several increasing values of n. Now, if you plug in 1, it's easy enough to see that 1 plus 1 over 1 would just be 1 plus 1, or 2, to the power of 1 is 2. But it's going to get a little complicated after that. So I would like to consult my calculator. And I think I'll just use my handy-dandy Desmos calculator. Did you know that Desmos makes an app for their calculators? So if you don't have the app downloaded on your cell phone, it's something to consider. All right, so I've already got the first expression. I could double check that. 1 plus 1 over 1 to the power of 1. You can clearly see that that's 2. Now what I'm going to do for the remaining expressions is I'm going to copy and paste. Control C for copy, Control V for paste. And then I'm just going to change this number. So this would be a 10, and this would be a 10. And I'm going to record this on my paper. And I'll just record it out to 4 decimal places, 2.5937. Don't have enough room for all of those digits. Okay, so now I'll just add more zeros to the value of n. So this would be 100, and this would be 100. I'll record this number, 2.7048. Control V. So now I need this denominator to have 3 zeros and the exponent to have 3 zeros. So I'm recording this value, 2.7169. Okay. Control V. So now I have 4 zeros, 1, 2, 3, 4. 1, 2, 3, 4. So now I have 2.7181. It's interesting how the numbers are not that different. Okay, so now I'm going to have 5 zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so 2.718. I guess I could round that 2 to a 3. All right, so now I need 6 zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2.7183 again. What am I up to? 7 zeros? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2.7183. This is starting to converge, I would say, to this number, 2.718, and so on. You can see that the numbers are starting to converge to the same thing, okay? So in the last ones, I had the same digits. This is a special number in mathematics and science. This number is called E, all right? As n approaches infinity, or as n gets larger, this value approaches some number that we call E, all right? It is the natural base, 2.7183, and so on. So this is something that we use in nature to describe lots of things. It's quite interesting how this number just continues to show up. Now, a logarithm whose base is E is called a natural logarithm. Now, let's not confuse this with a common logarithm that we learned about yesterday. A common logarithm has a base of 10. A natural logarithm has a base of this special number that we call e. So it's written log base e of a, and we have a little shorthand for it. We can't use the same thing we use for a common logarithm, obviously. Remember, in a common logarithm, we still write log, but we don't put a base at all, and we understand that that's 10. For a natural logarithm, we write ln, okay? Natural, it stands for log base natural of a. All the properties of logarithms that exist for bases other than e also exist for natural logarithms, okay? So let's take a look at this next section. We have some logarithmic expressions in different bases, 3, 2, and 5. And remember, we learned yesterday that we could calculate these using this change of base formula with the common logarithm of base 10. So I could write log of 20 divided by log of 3, and I could calculate the value of log base 10 of 20. Remember, that means 3 to some exponent is equal to 20. Now, that's obviously going to have to be a decimal because 3 squared is 9 and 3 to the third power is 27. So somewhere between 2 and 3, we would find the answer to this one. Now here I've got log of 116 and the base is 2. Now I could actually figure this out without a calculator because I know that 2 to the power of negative 4 would give me 1 over 16. For this one, I could do log of 15 divided by log of 5. 5 to what power is equal to 15? Well, 5 squared is 25, so this is going to be less than 2. And the point of this little table is to show that you could, instead of using common logs, you could also use natural logs the same way. Okay? Whoops, not log, ln. ln. I keep writing log. This is supposed to be ln. My bad. I'm so used to writing log. So I'm writing ln of 15 over ln of 5. So I'm just going to show that those are going to be the same. So let's go back to our handy dandy calculator. So I could say log of 20, whoops, that's not 20, divided by log of 3. And I see that that is approximately 2.7, I'll just call, well, I should say 3 probably. I'll call it 2.73. But I want you to notice that if I use natural log, ln of 20, divided by natural log of 3, you get the exact same number, approximately 2.73. All right, in the next one, we have log of 1 over 16. Whoops, I need to divide by log of 2. And that is -4, just like I thought. So let me show you how if I use a natural log, ln of 1 over 16, divided by a natural log of 2, it's the same. So you can use them in very similar fashions. And just to complete our table, let's do log 15 divided by log of 5. Okay, just as I suspected, it's a little more than 1.68. And with natural logs, so your calculator understands common logs, natural logs, and e itself. All right, let's go back to our notes. All right, so it says, what can you conclude about the values of log base b of a and log a divided by log b using base 10s and log a divided by log b using natural logs? And I think we can see that they're all going to be equivalent. So you could take the log of any base. You could use the change of base formula and write it with common logs or natural logs. Now I'm going to take a moment to explain to you why whenever I write the log, L-O-G, I always put it in cursive, and I want to explain why that is. If I don't put it in cursive, when I write L-O-G, sometimes it looks like 10G. So I put it in cursive just to avoid that. And the same thing with the natural log. LN, it looks like 1N. So that's why I put them in cursive, so that it's very clear that I'm actually talking about logarithms. Just a little suggestion for you. Avoids confusion. All right, let's get to this. I like these problems. It says, find the value of x in each of the logarithmic equations below by rewriting the equations as an exponential equation. So we're going to solve these exponential functions, and these are fun. Okay. So remember, this little base, he doesn't like being little. So he swings over and beats up this big number over here. And so we would write this as 9 to the power of negative 2/3 is equal to x. Okay. Now, what does this mean? Well, it means 1 over 9 to the positive 2/3 power. All right. Actually, I'm looking at this and I'm seeing that what this means is 1 over the cube root of 9 squared. And we're not going to be able to solve that without using some sort of calculator. So we would need to type this in our calculator. But that's okay. We can certainly do this. So let's go to our calculator. And I'll just type it in the way it was written in the first place. 9 to the power of, and I'm going to put this in parentheses, negative 2/3. So I can see that x is a decimal, which is kind of where I was going with that. I was like, this is not going to be easy to calculate. So I can just say that x is approximately 0.23. They didn't tell me how to round, so I'm just going to round where I think I should. Okay. Now, for this one, I want you to remember that when you have a natural log, it means a logarithm where your base is the number e. E is not a variable. E is the number approximately 2.7. So then the e swings over and beats up the 3. So e to the 3rd power is x, and we're clearly going to need our calculator for that. So I can go back here. E to the power of 3. And again, notice the Desmos calculator recognizes that E is a number. It understands that. So I can say that X is approximately 20.09. I'll just round to 2 decimal places because I can. All right, let's look at the next ones. Getting a little more complicated here. So we're going to do 3 to the power of negative 3 is equal to 2x plus 1. Now this I might actually be able to do. I know that this means 1 over 3 to the third power. I know that 3 to the third power is 27. Now I'm going to go ahead and subtract 1 from each side. So I could think of 1 as 27 over 27. So that when I do the subtraction, it would be negative 26 over 27. And then when I divide by 2, this would become 54. Now, if you wanted, you could just leave it 3 to the negative third, subtract 1, and divide by 2, and you would get the same answer. So let me explain what I mean over here. So 3 to the power of negative 3, you could just leave that. Then you would subtract 1 from each side, and then you would take that whole thing and divide it by 2. And you would get this number. Well, let me show you that that's the same as negative 26 divided by 54. So they're the same, and you could actually click this button over here and convert. I guess it reduces, doesn't it? Negative 26 over 54 does reduce to negative 13 over 27. Or you could leave it as a decimal, and it's totally fine. We didn't really receive more instruction as to how we should leave our answers. But if I am going to leave it as a fraction, I should certainly reduce it. Boom. All right, so this video hasn't been exactly smooth, but hopefully you're getting it. Okay, so 25 to the power of x is 5 square roots of 5. Let's think about this. Now, I know that 25 is 5 squared. And I know that this means 5 to the first power times 5 to the 1/2 power. The square root of 5 means 5 to the 1/2. So I would multiply powers here. Here I would add powers. 1 plus 1/2 is 3/2. So I know that 2x is equal to 3/2. And multiplying both sides by 2 gives me that x is equal to 3. I like it. Now, the other thing that I could have done is just, since x is equal to log base 25, actually, I don't think this would do logs of different bases, but I could go here and remember, to the right of the 9 on the Inspire calculator, you have these templates, and I could use this log template, and I could say log base 25 of 5 square roots of 5, and you get 0.75. How is that? Oh, y'all, I did math wrong. Let's go back here. This is not my morning. I wasn't supposed to multiply by 2. I was supposed to divide by 2. And when you divide $1.50 in half, you get 75 cents. Man, I'm a little rusty this morning. All right, let's see if I can do these last two without making a mistake. What do y'all think? It's okay. It's good for you to see me make mistakes. All right, so I'm going to solve for x. So one of the things I could do is I could just subtract 2 from each side, and I could just type that in my calculator. But I'm going to save that method. Let's see, if I did 2 to the power of x plus 2 equal 9. Well, that's not really helpful, is it? because I can't write 9 as a power of 2. So I'm just going to use this expression. So since I need a different base, I will do this template. So log base 2 of 9. Now the minus 2 is not really part of a logarithm. And so x is approximately 1.17. If I can make this number have the same base like I did over here, I could see that I could make these all base 5s, and that was working out nicely. Just didn't work out for that one. Okay, here's another one with a natural logarithm. Remember, this simply means log base e of x plus 3 is equal to 5. So e to the power of 5 is equal to x plus 3. I could simply subtract 3 from each side, and that's my expression that equals x. So once again, I could use any calculator for this one. So e to the power of 5 minus 3. So x is approximately 145.41. It's worth noting that e is a decimal that is non-terminating and non-repeating. It never ends and there's no pattern to it. That's called an irrational number. So you will always have to have a decimal for expressions involving the number e. All right, good luck, everyone.